In 2022, NASA's DART probe struck the asteroid Dimorphos, marking the first planetary defense test in history. This bold experiment aimed to determine if we can deflect an asteroid should one be discovered on a collision course with our planet. However, a follow-up mission is needed to analyze the effects of that impact in detail, which will be provided by the European probe HERA, launching in just a few days. So here's everything you need to know about this important mission. But how can we prevent an asteroid impact? Until 40 years ago, this question wouldn't even have been raised, as few were concerned about such an event. However, our understanding has radically changed. We've learned that the dinosaurs were wiped out by a planetary impact, and that events like the Tunguska explosion in 1908 were caused by celestial impacts. We've also witnessed more recent impacts, such as the one in Chelyabinsk in 2013, and the collision of comet Shoemaker-Levy with Jupiter in 1994. These events made us realize that the solar system is much more dynamic than we had imagined. By monitoring near-Earth asteroids, NEAs, we've discovered that not only can they impact, but over the long term, they do so with some frequency. This highlights the need to equip ourselves with so-called planetary defense techniques to prevent an impact and the catastrophic consequences that could follow. Before we continue, we invite you to give this video a like to support us with YouTube algorithms. If you haven't already, subscribe and activate the notification bell to avoid missing our upcoming content. There are various planetary defense techniques we can consider, all with the fundamental goal of diverting an asteroid from its trajectory at the right time and place, thus preventing a future impact. One of these techniques involves using so-called gravity tractors, based on a rather simple concept. A very massive spacecraft is placed near the asteroid, and by firing its engines, the spacecraft's gravity pulls the asteroid off its trajectory through slow but steady acceleration. An alternative technique involves solar furnaces, which use the sun's energy to generate an acceleration by concentrating it on a specific point of the asteroid's surface. Alternatively, a more rapid impulse could be applied to the asteroid, making it veer off its trajectory abruptly. This can be achieved through explosives, such as nuclear bombs, or through a kinetic impact, as in the case of DART, Double Asteroid Redirection Test. DART was the first planetary defense test in history. We've discussed it in previous videos. Essentially, the idea is quite simple. A kinetic impact involves a projectile probe crashing into the asteroid, rapidly transferring its energy to the asteroid and shifting it off its path. This way, we can prevent an impact if we detect an asteroid on a collision course with Earth. The target of the test was Dimorphos, a small asteroid 177 meters in diameter, part of the 65803 Didymos binary system. Being a binary system means that two asteroids orbit each other, bound by gravitational force. This choice was made because it's easier to alter Dimorphos's orbit around Didymos than divert an asteroid around the Sun. This makes the operation more manageable and, above all, easier to measure in a later phase. The test was successful, and now Dimorphos takes 33 minutes longer to orbit within its system. Numerous studies on that event have been published, including models and simulations of dust dynamics and asteroid structure, but a direct investigation is still missing to fully understand the impact's effects. This includes assessing the current state of the asteroid, whether it partially broke apart, changed shape, or developed a crater, and much more. This is why the European Space Agency's HERA mission was conceived. The idea for HERA emerged alongside the DART mission in 2013 as part of a joint NASA-ESA initiative. Originally, the mission was called ADA, Asteroid Impact and Deflection Assessment, and specifically targeted Dimorphos. NASA would build DART, while ESA would develop an orbiter called IMIM, which would orbit the asteroid to capture and study the impact directly. However, ESA withdrew for budgetary reasons, and NASA continued with the DART project. In the following years, ESA revived the project with HERA. By then, it was too late to launch both probes together, so HERA will arrive after the impact to study the post-impact effects. HERA's launch is scheduled for October 7th, aboard a SpaceX Falcon 9 rocket from Cape Canaveral. However, this date might change, so we encourage you to follow the agency's updates for any potential adjustments. Arrival at the asteroid is expected in 2026, which will take some time. HERA's goal is clearly to create a portrait of the asteroid after the impact. This information is extremely valuable for understanding planetary impact dynamics, a phenomenon we study in various contexts but rarely get to observe directly. In fact, we cannot reproduce a planetary impact in a controlled laboratory setting. In this case, Dimorphos itself will serve as our lab. Thanks to DART, we've conducted a controlled planetary impact, and now we can study its effects directly in the field. The primary objective is to understand how the energy transfer from DART to the asteroid depends on certain intrinsic characteristics of the asteroid. For instance, some asteroids are known as rubble piles, meaning they are accumulations of debris held together by gravity. This implies they have voids inside that could absorb part of the energy, making the kinetic impact less effective. It's like hitting a soccer ball with a punch. If the ball is fully inflated, it absorbs the blow, but if it's completely deflated, it may not budge at all. There will be many more data to gather, such as whether a crater was created, its size, and the asteroid's structure itself. It's possible Dimorphos deformed after the impact without forming a crater. To achieve these goals, HERA will be a cube measuring 1.5 meters per side, powered by solar panels and equipped with highly advanced scientific instruments to study the asteroid from all angles. One of HERA's main instruments will be a pair of asteroid framing cameras, AFC, two identical cameras that will be used to capture high-resolution photos of the asteroid from about 10 kilometers away. These cameras will provide a resolution of 1 meter per pixel, allowing detailed examination of the asteroid's surface. Another key instrument will be the laser altimeter, PAL, which uses a laser to scan the asteroid's surface and create a detailed map of its shape and geological features. This mapping will be crucial for assessing the impact's extent and the asteroid's morphology. HERA will also carry the Thermal Infrared Imager, TIRI, a Japanese camera developed by JAXA, which operates in infrared mode. This instrument will be used to map the asteroid's temperature, providing critical data about its thermal state and interaction with sunlight. Finally, HERA will be equipped with a hyperspectral imager, HYP, designed to study and map the chemical and mineral composition of Dimorphos's surface. With these tools, scientists will be able to obtain detailed information about the asteroid's composition, which is essential for understanding its origins and history. In addition, HERA will carry two CubeSats, named Milani and Juventus. These small, lightweight modular satellites will weigh about 12 kilos each and will be released from HERA before arriving at the Didymos system. Both CubeSats are equipped with cameras and scientific instruments to complement HERA's analysis, such as a radar on Juventus and a visible infrared spectrometer on Milani. At the end of their mission, both CubeSats will land on Dimorphos, allowing scientists to evaluate the asteroid's mechanical properties and the dust environment near its surface. In summary, the HERA mission aims to collect fundamental data for our understanding of asteroids and planetary defense. There will be much to discover and learn from this mission, and we expect results that could revolutionize our approach to Earth protection. Now we just have to wait for HERA's launch and its arrival at its target. The mission will not only provide crucial data on how planetary impacts work, but will also help improve planetary defense techniques that we may need to use in the future. Thanks for following this deep dive into the HERA mission. If you're passionate about astronomy and want to stay updated on this and other space projects, we invite you to subscribe to the channel and stay tuned for future videos.